All right, in Chapter 8, we're going to be looking at basic concepts in chemical bonding. And so we're going to be interested in the different kinds of bonding and how we measure it and how we draw structures and all kinds of fun stuff. So we're going to start by looking at the different types of chemical bonds. And we've already talked about some of these, so this won't take too terribly long. First, chemical bonds are simply the attractive forces that hold atoms together in molecules and hold ions together in crystals. Ionic bonds are simply electrostatic attractions between oppositely charged ions. Covalent bonds are shared pairs of electrons that hold atoms together in a molecule. And those two are the ones that we've talked about before, and we're going to talk a lot about ionic bonds and covalent bonds going forward. And then finally, metallic bonds. These are the sharing of many detached electrons between many atoms. And so this is a special kind of bonding. We're going to talk about this, I believe, in chapter 11 or 12. I forget which one. So we want to start with Lewis symbols and the octet rule. And Lewis symbols were something that were developed by a chemist named G.N. Lewis. And it was simply a method to denote the potential bonding electrons by using one dot for every valence electron around the element symbol. All right, and so here are some Lewis symbols for, these are the period 2 and 3. So period 2, we've got lithium, has one valence electron. And I think we talked about this in the previous chapter, but the group number will tell us the number of valence electrons. And the electron configuration also tells us the number of valence electrons. And so we've got one valence electron, so we have one dot. With two valence electrons, we'll get two dots for both beryllium and magnesium. For three valence electrons, we'll have three dots. And you'll notice that we put one on each side until all four sides are filled up, as we have here on carbon and silicon in group 4. And then now we start to share sides, so we have pairs of dots, or pairs of electrons. So here we've got 5 electrons around phosphorus and nitrogen, 6 around oxygen and sulfur, 7 around fluorine and chlorine, and 8 around our noble gases, neon and argon. So now we want the octet rule, and the octet rule says when forming compounds, atoms tend to lose, gain, or share electrons so that they are surrounded by 8 valence electrons. And we'll find that this is true for atoms in period 2 and below on the periodic table. In period 1, like hydrogen, it can't have 8 electrons. So let's look at number 7. All right, so number 7. So what are valence electrons? Well, valence electrons are simply outer shell electrons. Okay, the next question is, how many valence electrons does a nitrogen atom possess? Well, nitrogen is in group 5, so therefore it has 5 valence electrons. An atom has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p2. How many valence electrons does this atom have? All right, well, we just look in the highest electron shell, the highest principal quantum level. So that's level 3, and we've got 2 plus 2, so that's 4 valence electrons. All right, the next question is, what is the octet rule? Well, I'm going to go back to this page, and then I'm going to pause and then write it down and then go back to the other page. Okay, so there we go. I just wrote down what was on that page. When forming compounds, atoms tend to lose, gain, or share electrons so that they are surrounded by 8 valence electrons. How many electrons must a sulfur atom gain to achieve an octet in its valence shell? Well, remember, an octet is 8. We just need to look and see how many sulfur has. Sulfur is in group 6, so it needs to gain 2 electrons. So we'll put gain 2 electrons. All right, if an atom has the electron configuration 1s2, 2s2, 2p3, how many electrons must it gain to achieve an octet? Well, we just look at its outer shell, the 2s and the 2p. We've got 2 plus 3, so that's 5. It must gain 3. All right, so it must gain 3 electrons to get 8 in its outer shell. Okay. So we now want to look at ionic bonding. Not to be confused with ionic columns. Ionic bonding, ionic bonds are typically formed between metals and nonmetals. However, you can also get an ionic bond between a metal and a polyatomic ion, or even between 2 polyatomic ions. When it's between a metal and a nonmetal, we'll find that the metals lose electrons to empty out their outer shells, and nonmetals tend to gain electrons to get a full octet. An example of this is sodium plus chlorine atoms to give a sodium ion plus chloride ion. So when we do that, the sodium has 1 electron in its outer shell. It loses that 1 electron, and chlorine has 7, and it gains that 1 electron. So we end up with an emptied out outer shell for sodium and a full outer shell for chlorine, for the chloride ion. We're going to find that the sodium actually has a full outer shell now, but it's no longer the level 3 shell, it's the level 2 shell. To demonstrate this, I'm going to show you a diagram, an electron configuration energy diagram that we did back in chapter 6, and we did some of these in chapter 7 as well. So sodium has the electron configuration, and we had done this one previously, 1s2, 2s2, 2p6, 3s1. So there's 11 electrons for sodium, and that is its electron configuration. The electron configuration for chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. All right, so there are all of the electrons for chlorine. So now what happens is sodium is going to lose this electron that's in the 3s subshell, and chlorine is going to gain that electron in the 3p subshell. So that electron is going to get transferred from the chlorine, or from the sodium over to the chlorine. So here it goes, over animated graphic. All right. And so now the electron configuration for sodium ion is 1s2, 2s2, 2p6. That sodium ion is now isoelectronic with neon. And we'll find that that's what we mean to have a full octet or a stable octet, is to have something that is isoelectronic with a noble gas. So in this case, 1s2, 2s2, 2p6. We'll see now our outer shell is the level 2, and that we have 8 electrons there. Our outer shell for chlorine is level 3, and there are now 8 electrons there, 1s2, 2s2, 2p6, 3s2, 3p6. For a total of 18 electrons, that is now isoelectronic with argon. All right, now that we've done that, we want to look at problems 11, 14, and 15 on the in-class assignment. So on number 11, we want to write Lewis symbols for atoms of each of the atoms or ions. Something weird happened there. We want to write Lewis symbols for each of these. Okay. So all we have to do is to look at what group number it is in. Aluminum is in group 3. Since aluminum is in group 3, it has 3 electrons, so we'll put 3 dots. In case you're wondering, it doesn't particularly matter which three sides you put the dots on. All right. Bromine, all right, we got a bromine atom. Well, bromine is in group 7. Since it's in group 7, we're going to put 7 dots around the bromine. So 1, 2, 3, 4, 7. Again, it doesn't particularly matter where the lone dot is. All right. Potassium, that's an alkali metal. So here's potassium. It's in group 1. So it's going to have 1 valence electron. So we'll put K with a single dot. And then here is strontium. Strontium is in group 2, but I'll show you where. There's strontium in group 2. Since it's in group 2, we'll put 2 dots. So SR dot. All right. Magnesium 2 plus. Well, magnesium is in group 2, but because it's lost 2 electrons, then we don't really need to put the electrons around it, so we can just put Mg2 plus. It'll be the same as the electron configuration there. You sometimes will see people put 8 electrons to represent the 8 electrons that are down in period 2. However, I tend not to put them because they don't really participate. All right, and now for phosphide. Well, phosphorus is in group 5, and since it's in group 5, it has 5 valence electrons. If it picks up 3 more, it will have a full octet. So phosphorus will put 8 electrons around it. And then typically the way it does it in the textbook is it will put the full charge on that atom. So they'll put the 3 minus right there. So use Lewis symbols to represent the reaction that occurs between magnesium and bromine atoms. Well, magnesium has 2 electrons, so 2 dots. And then the bromine atoms has 7 dots, and there's 2 of them. So I'm going to go ahead and draw both of them. Okay. And when we make the new bond, well, we have 2 electrons to get rid of from this metal, and we've got 7 electrons on each of the bromine atoms. So that means each bromine can accept 1 of those electrons. So each bromine can accept 1 of those. So this will accept 1, and that will accept 1. So we'll end up with magnesium 2 plus a Br, all right, with a minus. And sometimes I'll put the brackets around it. And then I'm going to put another bromide there with a minus. All right, and so that's a representation of the reaction that occurs. Looking at problem number 15 on the in-class assignment, predict the chemical formula of the ionic compound formed between each of the following elements. So for aluminum, we know that aluminum has 3 valence electrons because it's in group 3, and fluorine has 7. All right, so there's 7 there. So that means that each fluorine can accept 1 electron, and aluminum has 3 of them. That means that we're going to need 3 of the fluorine atoms in order to make this work. So we'll have AlF3. Now, if I had asked you to do this back in chapter 2, you would have said, well, I know aluminum forms a 3+ charge, and fluorine forms a -1 charge, and then from that, you could have gotten the formula. This just provides another approach, sort of coming at it from the other direction to figure out what the formula is going to be. For potassium, the potassium ion, or potassium atom, has 1 electron, and sulfur has 6 because it's in group 6. So that means that each potassium can donate 1 electron, and sulfur needs 2. We're going to need 2 of those potassiums to form potassium sulfide. All right. Again, if you had done this way back in chapter, chapter 2, we would have said, well, potassium forms a +1 and sulfide is 2-, and so therefore this is going to be K2S when we do that. All right, aluminum again has 3 dots, and oxygen has 6 dots. All right, so oxygen needs 2, aluminum can get rid of 3, and we're not going to be able to do this where we just keep one at 1 and the other with some multiple. So the way that we can do this is if we have 2 of the aluminum, that would give us 6 total electrons that we would be getting rid of, and then to take 6 electrons, we would need 3 of the oxygens. So that would be Al2O3. Again, if we were back in chapter 3, we would have said aluminum is 3 plus, oxide is 2-, and we would have gotten that formula easily. Okay, so now we want to look at the energetics of ionic bonding. As we saw in the previous chapter, chapter 7, the ionization energy of sodium is 496 kilojoules per mole. So at 496 kilojoules per mole, 496 kilojoules per mole, that's how much energy it takes to remove 1 electron from 1 mole of gas phase atoms to form gas phase ions. And then the electron affinity of chlorine is negative 349 kilojoules per mole. And so that one is how much energy we get when we add that 1 electron to the chlorine to give chloride ions. Again, all gas phase. And if you look at these two numbers together, well, we've got positive 496 and negative 349. And you might think that that should give us an endothermic reaction. However, that's definitely not the case. We have a decidedly exothermic reaction when we put these together. And so I want to show you a video of that exothermic reaction. So if you click on this link, you will open up this video. And so here's the video, and I'm going to go ahead and click on that.
We've asked Lonnie to demonstrate the formation of an ionic bond. In this case, the bond between sodium and chlorine in sodium chloride. So Lonnie's filled a beaker with elemental chlorine. That's chlorine gas, Cl2. It's a yellow gas. He'll also use solid sodium metal. Solid sodium metal is a shiny silver metal that's very soft. He can actually cut it with a knife. Sodium metal is very reactive. It will react in air and water, so it's stored under hexane. He'll pull off a small chunk and immediately store it under hexane while he prepares the rest of the experiment. Now, to get the reaction to go, he'll want to clean the sodium, make the surface very clean, and warm it slightly to help the reaction proceed. He'll do that by placing the sodium in a spatula and then warming it over a flame to clean the surface and to get the sodium warm enough to initiate the chemical reaction. Now, the reaction between sodium metal and chlorine gas proceeds, but we know the ionization energy of sodium is greater than the energy released, the electron affinity, when chlorine accepts electrons. So the reaction goes because the positive ions formed on sodium and the negative ions formed on chlorine are drawn together, a Coulombic interaction, to form an ionic bond. The formation of that ionic bond, plus and minus charges attracted together, releases energy, and that's the driving force for this chemical reaction. And you can see that it's exothermic. Energy's being released. Bright red glow, typical of emissions from sodium. Now the reaction between sodium and chlorine, of course, forms sodium chloride. We typically know that as table salt. And Lonnie's prepared some in advance. He has white table salt, purified, that he can show us. There it is, purified in advance from Lonnie Laboratories. And Lonnie tells me the salt that he makes in Lonnie Laboratories is far superior to any salt that you can buy in the store. So what does he have to do now? Lonnie's going to demonstrate, clearly hasn't had his breakfast this morning, that Lonnie Lab salt far superior to any salt you could buy in the store.
Don't eat in the lab.
Thank you, Lonnie, for that demonstration that sodium chloride, an important spice and food flavoring. And when you make it yourself, the satisfaction is so much more.
Okay, well, so that is Lonnie Laboratories, and clearly he's kind of having a little bit of fun there. But you can see that was definitely a very exothermic reaction. And I just like showing that video. I kind of get everybody's attention. So we want to go back over to our presentation and figure out why it is that we've got this exothermic reaction, but then if we add these two things together, we're getting an endothermic number. Well, the problem is that it's a lot more complicated than what we've drawn here. So in order to get this, we need to look at something else that we refer to as the lattice energy. So the lattice energy is this definition. It is the energy required to completely separate 1 mole of a solid ionic compound into gaseous ions. For sodium chloride, the lattice energy is this. So sodium chloride, and then we convert that into gas phase sodium ions and gas phase chloride ions, and that gives us a delta H of 788 kilojoules per mole. It takes a lot of energy to get the lattice energy of something. And really, it's just saying how much energy is holding all these ions together. Now, the magnitude of the lattice energy is going to be given to us by Coulomb's law. And Coulomb's law tells us that the energy, the attractive energy that's holding the ions together, is equal to a constant. This is called the, well, it's just called the constant. I forget what the name of it is. Times the charges of the ions in coulombs divided by the distance between the nuclei of those ions in meters. And we're not going to actually do this calculation. As fun as that would be, we're not going to do this calculation. Problem number 20 is simply to write down the definition of lattice energy. So I'm going to do that, and then I'm going to switch over. Okay, so I managed to write this out. I had trouble with my pen, so it looked a little weird here. I had to switch the little cartridge on my ink there. But that is our definition of lattice energy. Again, you can read it more easily up here on the screen. That is what goes in that space. So what we want to look at here is a table of some lattice energies for some ionic compounds. You'll notice here, let's look at sodium fluoride, chloride, bromide, and iodide. You'll notice the only thing that's changing is, are those anions, fluoride, chloride, bromide, and iodide. Well, fluoride is really small ion. Chloride's bigger, bromide's bigger, iodide's even bigger. And you'll notice that as it gets bigger, the lattice energy decreases. Well, if we go back and look, as the distance increases, in other words, as the atom gets bigger, the distance between the nuclei will increase. That will decrease the amount of the lattice energy. So bigger ions will give us a larger lattice energy. The other thing that will give us a larger lattice energy is if we have greater charges. So all of these over here have a +1 charge on the cation and a -1 charge on the anion. But over here, we've got magnesium chloride. We've got a +2 on the cation and -1 on each of the anions. And there's a lot of interactions going on there. For these, it's +2 and -2, and you'll see that they are much larger. Well, again, the reason for that is that if the charges increase, then the electrostatic energy will also increase. All right, so lattice energy increases as you increase the charge on the ions and as you decrease the size of the ions. So if you decrease this, you decrease the size, so if we're going this way, we're going to get higher lattice energies. Here, we're changing the fluoride, chloride. This one, we're changing the cation. So it works for either cation or anion. So we want to look at 21. And 21, on 21, we're looking at the ionic substances, Kf, CaO, and SCN are isoelectronic. They have the same number of electrons. Examine the lattice energies for each of these substances and account for the trends you observe. So we're going to write down Kf and then CaO and SCN. So we're going to put those three things right there. And then right below, I'm going to put the lattice energy. So let's go back and find those lattice energies. So for Kf, it's right here at 808. So 808 kilojoules per mole. Calcium oxide is over here at 3414. And scandium nitride at 7547. All right. So 7547. So now let's go back and look at this and we will see, all right, well, definitely these are much bigger. And the reason that they're much bigger is that the charges are bigger. If you look, potassium is +1 and fluoride is -1. And if we go and look at that formula, equals the kappa times Q1 times Q2 over the distance. So if you look, +1 times -1 is going to come out to -1. This one is +2, and this one is -2. So +2 and -2, you multiply those, that's going to come out to 4. So this should be about 4 times bigger than the 808 here. Scandium is +3, and nitride is -3. So +3 times -3 would come out to -9. So we would have a much big, this one should be about 9 times as big. Now we can look and see how much bigger it actually is. It's not quite, it's a little bit more than 4 times and a little bit more than 9 times, but you'll see it comes out pretty close. So 3414 divided by 808 gives us 4.23. So we'll see it's a little bit more than 4 times as big. And then 7547 divided by 808, and that gives us 9.3. So it's a little bit bigger than 9 times as much. Now, the reason it's not exactly 4 and exactly 9 is because of the size of the ions are slightly different as well. All right, so let's go back over here. We've done number 21. And so now we want to look at the Born-Haber cycle. And so the reaction that we talked about a little bit earlier, which is the exothermic reaction of sodium plus chlorine getting converted into sodium chloride, that is an exothermic reaction. And we wanted to see why it was that when we added our ionization energy and our electron affinity and we got a positive number, why didn't that account for everything? So I want to do Hess's law and add together 5 different equations. There's 5 different processes that are occurring over here. So add together those 5 different equations so that we could come up with the overall energy for this process. Now, to convert sodium into sodium gas, since this is elemental sodium, all right, that's elemental sodium, that's going to be the enthalpy of formation. And so we can just go over and look at the appendix and scroll down and find sodium. And sodium gas is right there at 107.7. You may not be able to read it very well, but trust me, it's 107.7. All right, 107.7. Then we want to take the Cl2, half a mole of Cl2, and convert it into 1 mole of chlorine atoms, again, all in the gas phase. Again, we're going to want the delta H of formation, and so just to show you where I got that, there's chlorine, and you'll see 121.7. I could make this bigger. There you go, 121.7. All right, and then here, this is the ionization energy right there. And it's also endothermic. That's the ionization energy for sodium. And as you recall from chapter 7, that was 496 kilojoules per mole. And then for chlorine, the electron affinity is this one. We give one electron, 1 mole of electrons to that, and we will get negative 349, so it comes down in energy. And then our final one is, it's actually the opposite of the lattice energy. And remember, when you change the direction of a reaction, you change the sign. So here, we're going to get the negative of the lattice energy, and we'll get negative 788 kilojoules per mole. So now, we're going to add all 5 of those together. First, I'm going to cancel out things that are different on each side, or the same on each side, rather. So sodium gas cancels out. Chlorine atoms in the gas phase cancels out. The electron cancels out. Our sodium ion in the gas phase cancels out. And our chloride ion in the gas phase cancels out. And so here we get sodium plus chlorine gas gives us sodium chloride. And that's going to give us a delta H of negative 412 kilojoules per mole. So what do I want you to remember about this? Well, the thing I want you to remember about this is I want you to be able, if you were to look at a diagram that's like this, I want you to be able to remember what the ionization energy is, what the electron affinity is, and which one's the lattice energy. They will not be labeled as ionization energy, electron affinity, and lattice energy. They'll be labeled as some, delta H1, delta H2, delta H3, delta H4, delta H5. You have to be able to identify which one's ionization energy, which one's electron affinity, and which one is lattice energy. What this does, it explains the octet rule. Because the ionization energies are so large, once you run out of electrons in the outer shell, those ionization energies are so large that you wouldn't get that energy back with the increased lattice energy from having like a +2 charge. This is why we never see sodium +2 in a reaction. The only time we see sodium +2 is when we're looking up ionization energy. Okay, so that is for ionic bonding, and we're done with ionic bonding. And so now we're going to talk about covalent bonding in Chapter 8, Section 3. So when we're talking about covalent bonding, the first thing that we're going to look at is what makes up a covalent bond. And we're going to start with perhaps the simplest molecule that you can get in a covalent bond. And that simplest molecule is hydrogen. And so here, I'm going to show you the hydrogen molecule. So there's the hydrogen molecule, not very exciting. There's just a single bond in between, and we're going to talk about bonds here in just a moment. But there's a single bond in between those, and what makes up that bond is going to be the hydrogen, the nucleus of each hydrogen. So there's 1 proton in each nucleus, and there's 1 electron that goes with each atom. So there's only 4 particles that are in a hydrogen molecule. That's it, 4 particles. So in covalent bonds, the atoms share the electrons, and the bond between hydrogens in H2 is shared. There are several electrostatic interactions that we care about, and so those can be represented by the picture over here. And so we've got 2 protons and 2 electrons. There are the attractive forces between the electrons in the nuclei. So these are the red ones here. So there's 4 different attractive forces there. and the repulsive forces between the electrons, so the two electrons do push on each other, and the repulsive forces between the nuclei. So if the nuclei get too close, they will repel each other as well. For the bond to form, the attractive forces need to be greater than the repulsive forces. And that's it. Okay. Now, one other thing is that electrons don't behave like point particles. They don't behave like a point. And that's because electrons are non-classical particles. They have wave functions, and so they behave like waves, like orbitals that we talked about in chapter 6. And so they're going to look something like this, where we get this cylindrical electron density that's in between the two atoms. And that is our bond. All right, we're going to real briefly look at Lewis structures, and then we're going to come back to Lewis structures and do a whole bunch of them here in a bit. We draw Lewis structures to show which atoms are covalently bonded to each other in a molecule. We also want to keep track of where the electrons are. Single bonds are a shared pair of electrons, so one pair of electrons that's shared in between two atoms, and they are simply represented by a line between the atoms. We saw the H2 a minute ago. All right, so there's the hydrogen molecule, and here's the chlorine molecule, and we will see this a little bit later as well. Lone pairs of electrons, these are called unshared electrons. All right, so those are unshared electrons, and we will sometimes refer to those as just non-bonding electrons. They are represented by a pair of dots, just like we did in the Lewis symbols. All right, and then each atom usually has a full outer shell of electrons. In other words, it has 8 electrons around it. All right, so here chlorine, you'll see that there are 2, 4, 6, 8 electrons. We're going to count that one. The shared electrons get counted for both atoms. And then for this chlorine, 2, 4, 6, 8 electrons around it. Now, hydrogen can only have 2 electrons, and it can either have a bond or a lone pair of electrons, but it can't have both. And so here, each hydrogen has a duet instead of an octet. For multiple bonds, sometimes we'll get multiple bonds where we have more than one pair that is shared between two atoms. And so if we have 2 pairs shared between the 2 atoms, we call that a double bond. And in this case here, we've got carbon and 2 oxygens, and we end up sharing 2 pairs of electrons. Now, we're not going to draw our Lewis structures to look like this, where we have dots to represent the bonds. 1, it gets really, really messy. And 2, I want you guys to know better. So we're going to draw it where we have lines to represent the bonds. So here, this oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. Carbon has 4 bonds, so that's 8 electrons around it. And this oxygen also has 8 electrons around it. So that's our valid Lewis structure for carbon dioxide. So those are both double bonds. If we have 3 pairs of electrons shared, we refer to them as triple bonds. And if you're wondering, well, where does this end? How many bonds can we share? For the things we're going to look at, 3 is the maximum. However, I will tell you that there is such thing as a quadruple bond. You need some d orbitals. It's complicated. We're not going to talk about it right now. But here is a triple bond between the 2 nitrogen atoms and just elemental nitrogen. So there is a triple bond. All right, we now want to look at the concept of bond polarity and electronegativity. So the electrons in a covalent bond are not always shared equally. And so bond polarity tells us how unequal that sharing is. If you've got it completely equal, where the two atoms share the pair of electrons completely equally, so the electrons are right between the 2 atoms, then we call that a nonpolar covalent bond. If the electron, the pair of electrons, is shared unequally, then we'll see that the electrons are shifted a little bit closer to one of the atoms than to the other atom, and we call that a polar covalent bond. In bonds where the electrons are essentially completely transferred, we call those ionic bonds. And I've got an example of a nonpolar, a polar, and an ionic bond over here. So in F2, since they're both the same atom, there's no reason why the electrons would be pulled more to one than the other. We will find that this is a nonpolar covalent bond. Here, between H and F, the electrons are pulled more strongly towards the fluorine, and so this is going to be a polar covalent bond. In lithium fluoride, the lithium just doesn't keep the electrons very well, and the fluorine pulls the electrons towards it. Essentially, those electrons are completely on the fluorine atom. We're going to call that one an ionic bond. So an ionic bond is kind of like an extreme polar covalent bond. So one of the tools that we use to determine how polar a bond is going to be is something that we call electronegativity. Electronegativity is simply the ability of an atom in a molecule to attract electrons to itself. And electronegativity increases as you go up and to the right towards fluorine. So you'll see fluorine here is at 4.0, oxygen is at 3.5, nitrogen and chlorine are at about 3.0. And then as you get further away, you go all the way down here to cesium, and you'll see cesium is at 0.7. All right, so number 35 here is write the electronegativities for each of the following elements. So I'm going to go back to that table and write these numbers in. And then what is meant by the term electronegativity? Well, I'm going to go back to that previous page and write that definition. So we're going to go back over there. I'm going to pause the video and then write those things down, and then I'll unpause the video. All right, so I've written all those numbers and I've written the definition here. And so hopefully you have done that. If you've not, then pause your video right now and write those things down. But we're going to go back to this. On the Pauling scale, this thing was invented by Linus Pauling, famous chemist. So on the Pauling scale, what is the range of electronegativity values for the elements? Well, the smallest number is 0.7, and the largest number is 4.0. So that is the range. Which element has the greatest electronegativity? Well, that's fluorine at 4.0. And which element has the smallest electronegativity? Of the ones that we listed, it's cesium at 0.7. All right, now technically, if you go down a little further to francium, you may get a slightly lower number, but as we've talked about, francium is so dreadfully radioactive that we don't want to mess with that. All right, so now that we have these written down, we can refer to them when we're doing some of the other problems, so we don't have to keep coming back to this page. All right, so we want to look at polar covalent bonds. So electrons tend to have a greater electron density near the more electronegative element. All right. The result of this is that we get a partial negative charge on the more electronegative element and a partial positive charge on the less electronegative element. We represent the partial negative charge by putting a lowercase Greek letter delta with a minus right afterwards, and a lowercase Greek letter delta with a plus for the partial positive. The separation of charge is called a bond dipole, and we can represent a bond dipole either by putting the delta plus and the delta minus, or by putting an arrow next to the bond to represent which direction the bond dipole points. We will get the arrow pointing towards the more electronegative element. You'll notice also on the other end of that arrow, there's a little cross on the more positive side. So it looks like a little plus sign on the more positive side. So that is officially the symbol that we use for indicating a dipole. But again, you can equally represent the dipole by putting the delta plus and the delta minus. Typically, we don't like to put both. If we put both, that can get confusing. So to calculate the dipole moment, well, let me say something here, that the electronegativities, the whole point of the electronegativities is a way to estimate the dipole moment of a bond without actually having to go through the complicated calculations and experiments needed to get that bond dipole. So we can describe the two, when we have two equal but opposite charges separated by distance, we can describe that as a dipole moment. And we use the Greek letter mu for dipole moment, and that's equal to the charge separation times the distance. So how much charge is separated times the distance. Again, you have to do experiments to tell you how much the charge is, and you have to do other experiments to tell you what that distance is. So rather than do that, we use electronegativities as sort of a stand-in. And then the units for this are going to be in debye. So just as a note, you're not going to have to do this calculation, although I do think there's an example in the textbook. I was looking at one earlier. I know there's an example of it. So you're not going to have to do that. All right. So to estimate the bond dipole, we can just take the difference in electronegativity. The greater the difference in the electronegativity, the more polar the bond. So for example, we've got HF, HCl, HBr, and HI. And so hydrogen has an electronegativity of 2.1. Fluorine has an electronegativity of 4.0. That's a difference of 1.9. That means that's going to be a pretty polar bond. So if we look at our compounds, HF, HCl, HBr, HI, their bond lengths are given here, and then the electronegativity differences are given here. That difference in electronegativity is a pretty good estimate of the dipole moment. However, it's not perfect. And the reason it's not perfect is that it doesn't account for things like bond length and other stuff, sort of other factors that are hard to measure. But you can see that it's a pretty good estimate, and pretty good estimate is good enough for us. If you go on and you take a more complicated class, then you could look at how we calculate the dipole moment. But we're always going to use these electronegativities to give us a first quick estimate of the polarity. So, is a bond nonpolar, polar, or ionic? We can get a rough estimate whether it fits in one of these categories by looking at the difference in electronegativity. If the difference in electronegativity is between 0 and 0.4, we typically will call that a nonpolar covalent bond. Examples of this are going to include carbon-hydrogen, that's right at a 0.4 difference, carbon-carbon, which is that's 0 difference because they're identical, or any two atoms that are exactly the same, or if there's just a small difference in electronegativity, then it's going to fit into this category. Lots of molecules, lots of bonds will fit in this category. If we look at the difference in electronegativity and it's between 0.4 and all the way up to 2.0, we're generally going to classify that as a polar covalent bond. And examples of that include a carbon-oxygen bond, a hydrogen-fluorine bond, a carbon-chlorine bond, and there's many, many examples of this. All right, and the best way to figure it out is to look at the difference in electronegativity. Now, generally, if the difference in electronegativity is greater than 2.0, now the maximum possibility is 3.3 because we have 0.7 and 4.0, so our maximum is 3.3. If it's greater than 2.0, we're generally going to call that an ionic bond. All right, and examples of this are going to include sodium chloride, lithium fluoride, magnesium oxide. And I will warn you that there are molecules that are definitely ionic that have differences less than 2.0. And there are compounds that have differences greater than 2.0 that are still considered polar covalent. There are other factors that go into it, like bond length, oxidation numbers, melting points. Those are all things that can give us clue whether something is polar or ionic. If you have a really, really high melting point, it's probably ionic. And so, again, it varies. We're just trying to get an estimate here. So we're just trying to get an estimate. So we're going to look at number 40 and number 30 on the in-class assignment. And we want to arrange the bonds in each of the following sets in order of increasing polarity. So we'll need we want the electronegativity for each of these. Carbon is 2.5 and fluorine is 4.0. If you're wondering where am I getting these, it's from this chart that we wrote down. So 2.5 and 4.0. Oxygen is 3.5 and 4.0 for the fluorine there. All right, and then beryllium. Beryllium is, I'm going to have to look that one up. Beryllium's 1.5, and the fluorine is still 4.0. So if we look at the difference, this has a difference of 1.5. This one has a difference of 0.5, and this one has a difference of 2.5. So which one of those is the least polar? Well, the oxygen fluorine would be the least polar. All right. The next one is going to be the carbon fluorine bond would be more polar. And then finally, the beryllium fluorine bond, you would think that was going to be the most polar. Now, you might think with the 2.5 that beryllium fluorine bond should be an ionic bond, and that would be incorrect. It turns out that is definitely a covalent bond. And so this just goes to show that it's more complicated than just looking at the difference. But again, it gives us a good estimate. All right, oxygen is 3.0. Chlorine, 3.5. Chlorine is 3.0. So that's a difference of 0.5. Sulfur is 2.5. And bromine, bromine is 2.8. Yes, 2.8. So that's a difference of 0.3. And then carbon is 2.5, and phosphorus is 2.1. So 2.5 and 2.1. All right, just fix that real quick. And that gives us a difference of 0.4. So based on these numbers, we can get an estimate that the least polar is going to be that sulfur-bromine bond. And then next will be the carbon-phosphorus bond. And then next after that is going to be the oxygen-chlorine bond. That will be the most polar. But those are all pretty close to each other, and it is possible that one of these could be out of order because of bond distances. Okay, so next let's look at this. So 2.5 for carbon, 2.5 for sulfur. Well, that's 0, so that one's definitely going to be the least polar. Boron is 2.0, and fluorine is 4.0, and I'm going to double check to make sure I didn't goof that one up. Yeah, boron is 2.0, it's right there. So that gives us a difference of 2.0 for that one. Nitrogen is 3.0, and oxygen is 3.5, so that gives us a difference of 0.5. So our least polar bond is the carbon-sulfur bond, and then the nitrogen-oxygen bond would be more polar, and then the boron-fluorine bond would be the most polar. All right, so now we want to use our common sense on these. Which of these elements is unlikely to form covalent bonds? Well, we'll find that most covalent bonds have at least one nonmetal that's attached. Now, that's not universally true, and I can explain why that is. Well, I can explain why that is in one chart. And why that is in one chart is right here. There are some metals that have very high electronegativities. So if you have a bond between gold and sulfur, that is going to be a covalent bond. And in fact, a lot of these elements in here form covalent bonds because their electronegativities are pretty high. However, most of our metals that are over here and our common metals that we use all the time, or whatever, group 1 and group 2, those metals tend to form ionic bonds. So they tend to form ionic bonds. All right, I mentioned that because that tells you if you have a metal, it probably isn't going to form a covalent bond. So, so we look, which one of these are unlikely to form covalent bonds? Well, sulfur, nonmetal, that should form a covalent bond. Hydrogen, nonmetal, that should form covalent. Potassium is a metal. And so metals tend to not form covalent bonds. Argon's not a metal, but argon is a noble gas. And noble gases don't form any bonds, generally speaking. So argon won't form one. And then silicon, that's a metalloid, and that one tends to form covalent bonds. So the only two would be potassium and argon. All right. So that is going to be the end of this video, and we will do the next video is going to be looking at doing Lewis structures. So I'm going to make one video that's all drawing those Lewis structures. That's going to be a long video.